You know, there's a mathematical idea that is so fundamental it is literally hiding in plain sight all around us. It's called convolution, and you can think of it as the secret sauce behind how things blend, smear, and spread out in our universe.
So to get us started, just think about this for a second. What single mathematical idea could possibly connect all of the following things? They seem totally unrelated.
Okay, first up, a blurry photograph. You know how it works. The sharp points of light have been smeared out, kind of blended with their neighbors. How on earth do you describe that with math?
Or what about an echo? You have a single crisp sound that gets spread out over time, mixing with all these reflections of itself. It's a different kind of blending for sure, but the principle, it feels kind of similar, right?
And for our final clue, here's a real curveball you probably wouldn't expect: the grade on an exam. Believe it or not, this is also a blending problem. You're blending the probability of a student's knowledge with the probability of an examiner's expectations.
So the answer to our little puzzle is convolution. And at its heart, it's a surprisingly physical process. Really, it's all about three simple actions: flipping, sliding, and multiplying. Let's break that down.
Okay, so here's the formal definition. And I know, it might sound a bit dense at first, but the key phrase is right there in the middle: flipped and shifted. You basically take two functions, you reverse one of them, and then you just slide it across the other, measuring how much they overlap at every single step.
So, how does this actually work in practice? Well, let's take a really simple example: multiplying polynomials. We could just think of them as their coefficients, right? So here we have two sequences of numbers, one for each polynomial.
And here is the absolute key step. You take one of those sets of numbers and you literally flip it. You just reverse the order. Then you start sliding it across the other set, moving it one position at a time. This flip and slide motion, that's the unique signature of convolution. Now for each position that you slide to, you multiply the numbers that are lined up vertically. Then you just add all of those products together. That gives you one single new number for that specific output position.
You just keep doing this for every possible overlap, and the sequence of numbers you get at the end is your result. This new, blended set of numbers, that is the convolution of the first two. And in our case, it happens to be the coefficients of the final multiplied polynomial. Pretty cool.
Okay, so that was the mechanics of it. Now let's apply it to something a little more intuitive, like predicting the outcome of that exam we talked about, by blending two different probability distributions.
First, we have our student population. You know how it is. Some are really well prepared, most are about average, and a few are, well, underprepared. This chart just shows the probability for each of those three groups. Next up, we have our examiners. They've also got their own distribution. Some are super strict, most are average, and a few are pretty laid back. So the question is, what happens when we combine these two sets of probabilities?
So how do we actually combine these possibilities to figure out the most likely result? I mean, a great student might still have a tough time with a strict examiner, and a less prepared student might just get lucky with a laid-back one.
And here's the answer. By convolving the two distributions, we get this new one, and it shows us the probability of every possible outcome, from a big surplus of knowledge all the way down to a significant deficit. It just perfectly blends the two initial sets of probabilities.
So we've seen convolution blend polynomials and probabilities. But honestly, that's just scratching the surface. This idea is a true mathematical power tool, with applications all across science and engineering.
Let's just run through a few examples, lightning round style. In image processing, it's used to deblur photos. In audio engineering, it models echoes and creates filter effects. For structural analysis, it helps figure out how a bridge responds to stress. In statistics, it's used to find hidden patterns in data. It's even used to simulate the turbulence of flowing air. I mean, the applications are just incredibly diverse.
And that brings us to this absolutely perfect quote from the source material. Once you get to know something, you will find it everywhere. And man, that could not be more true for convolution.
All right, now for the really mind-bending part. We're about to see how the exact same math that describes something as mundane as a blurry photo also touches on the deepest, strangest parts of reality: quantum mechanics. Think back to that idea of smearing. On our big, macro scale, an effect spreads out locally, right? It influences its immediate neighbors. But at the quantum scale, the same mathematical family can actually describe non-local connections, a link between two particles that seems to totally ignore the space between them.
The sheer scale of this concept is just, it's incredible.
On one hand, you can use these mathematical tools to calculate a totally classical problem, like how a membrane bends under pressure. But on the other hand, the same family of math helps describe quantum entanglement, where two particles are linked in a way that just defies our everyday intuition. The same core ideas apply across these vast, vast scales.
And this is really the core of that quantum weirdness. When you have entangled particles, they essentially form a single system. If you measure a property of one particle right here, you instantly know the state of its partner, even if that partner is on the other side of the galaxy. It's this fundamental non-local connection.
So we have to end on this thought. If the same mathematics can connect a blurry photo to an echo, an exam grade, and the spooky nature of quantum reality, it just makes you wonder, right? What other hidden connections, all governed by these fundamental patterns, are still out there, just waiting for us to find them?